Hi there. The aim of this session is to introduce to you all radioactive decay half-life. Half-life describes the duration of radioactivity from a substance and the amount. I'm going to draw these things together. First of all, what I need you to think about is from what you know. So hopefully you should recognize that radioactive substances will decay at a random point due to some instability with the nucleus. Now we can't necessarily tell when this radioactive decay is going to take place. For instance, if we look at the couple of balls which is placed to one side of my head here on the screen. If each of these was a nucleus, and I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 balls, there would be at no moment in time I would be able to say that ball there is going to decay now. The reason for that is because, as we stated, this is a completely random act. I never know when a decay is going to take place. Especially with small numbers, there's no way I can make real predictions. Thankfully, when we're talking about radioactivity, we're talking about large numbers. Large number of atoms, which are radioisotopes. And because we're talking about such large numbers, it allows us to make some predictions due to the probability, the likelihood of decay taking place. So, moving up a scale, we'll introduce an idea to you. If I have 400 million undecayed nuclei, and I left them there, what would happen is that eventually 20 million of those nuclei would have decayed. If I wait a little bit longer, 10 million of those nuclei will be remaining undecayed, and if I wait a little bit longer, then 5 million of the remaining nuclei will be still to decay. Now, with these really large numbers, it suddenly means we can see certain patterns appearing. So here, it took 8 days for the amount of undecayed nuclei to drop from 40 million to 20 million. The same amount of time of 8 days it took from 20 million nuclei to decay by a further half, so there's only 10 million undecayed nuclei left, and then it would take a further 8 days for the 10 million remaining undecayed nuclei to break down to only 5 million undecayed nuclei remaining. So what we have here is that for this, and this is the example of iodine 131 as it happens, we have what's known as a half-life of 8 days. So half-life is the time it takes for half of the radioisotopes in a sample to decay. I've actually got two clear definitions which I'm going to try and use here. Half-life is the time taken for the number of radioactive nuclei in a sample to decrease by 50%. So that's the number of radioactive nuclei remaining that haven't been decayed away. We've also got to remember that with large numbers of nuclei, the likelihood of decay or a decay taking place is greatly increased. So that means the count rate, the amount of decays per second, is going to be directly related to the number of radioactive particles we've got. So the half-life is also related to the time taken for the count rate from a radioisotope to decrease by 50%. These are two really important definitions. Let's put this into practice a little bit more. Okay. What I have here is a graph, and the graph shows the change in count rate, counts per minute as it happens. Counts are the kind of, I guess, the number of beeps on a Geiger-Müller tube, for example. And it shows how this value decays over time, becomes less and less and less. And actually, if I look carefully, I can gain some information from this. The time takes the count rate to decrease from 80 per minute to 40 per minute is 2 minutes. So to go from 80 So 40 to go from this point to this point is 2 minutes. Now, if I look at the time it takes to go from 40 counts per minute to 20 counts per minute, this is also 2 minutes. So from this graph, I can recognize the half-life of the radioisotope as 2 minutes. So I can graphically identify what the half-life is when shown a curve like that. Okay. As it happens, this idea is tied up into something which you may be aware of, which is known as carbon dating. So all living things have a little bit of the radioactive isotope carbon-14, as well as normal carbon-12, which sits quite happily. Now, as our bodies continue to process things, we normally have about the same amount of carbon-14 in our bodies. But as soon as we die, there's no replacing the carbon. What we see is the carbon-14 slowly starts to decay away. As it happens, the half-life of carbon-14 is approximately 5,600 years. Now this is really, really useful, because if we can work out how much carbon-14 there was in the first place, using the ideas of half-life, we can work out how long ago the original bones, wood, paper or cloth came from a living source. I'll use an example of this as a typical question. So here's my example question. A fresh bone gives a radioactive count of 170 counts per minute. So this is my standard. Now, I've found some ancient bone of exactly the same mass, and this gives me a count rate of 50 counts per minute. Now, I've remembered that the background radiation due to the environment around us is always 10 counts per minute. How can I work out how old the bone is? Think about what you've just been told. Now, you can try and answer this question, but here's how you would do it. So, I know that the counts due to bones when fresh is 160, because I have to remove the background radiation, and ancient bones are going to be 40 counts per minute, because again I have to take into consideration the background radiation. So that means that the count rate has fallen from 160 counts per minute to 40 counts per minute. Now, one complete half-life would reduce the count from 160 to 80. Two complete half-lives would reduce the count rate from 80 all the way to 40. So that means I've gone through two complete half-lives to get to a count rate of 40 counts per minute, and that means that I can work out that this object, or these bones, are about 11,200 years old. So there's an example of the kind of question which you can come across. Just to wrap up this session, so you've got to think about, you can work out how old something is, or by working out how many, or the fraction of the fraction of the original amount of radioisotopes which are remaining, and then I can work out how many half-lives are taking place. So my question here is, what fraction of a radioactive sample is left after 4 half-lives? So think this through. 1 half-life, we get down to a half. 2 half-lives, we get to a quarter of the original. 3 half-lives, we get to 1/8. And 4 half-lives, we get to 1/16. So that means 1/16 of the original radioactive sample is remaining. And that concludes my session on radioactive decay half-lives.